introducing what is Stifford's method. Stifford's method basically is one approach. We are going to divide a continuous structures into a series of discrete, well-defined elements. I use this example as time to introduce what is discretization. You can break up whole structures into different well-defined elements. Set up the local displacement for displacement equations, and then group them together becomes the whole structural problems. Last time we introduced how to derive our first matrix, truss elements, but not yet finished. We need to continue our discussion today. And then this is a key part of Stifford's method, discretizations. This concept is very useful because this is actually what a computer doing. Computer discretize structures into different elements with well-defined nodes. They give you the result at the node. And then introduce some terms last time. What is known for a degrees of freedom? Degrees of freedom is also one important concept. Degrees of freedom means the possible movements at the end of a member. That means the degrees of the movements at the nodes. For truss elements, if you play with truss only support translational movements, horizontal, vertical. And then we have some movements equal to 0, some movement equal to non-zero. We call that constrained degrees of freedom and unconstrained degrees of freedom. We have to identify which degrees of freedoms are constrained, which are unconstrained, because this will affect you how to set up the solutions later. Set up the equations later. You can base on the support conditions to make judgment. Pin support, wall support, fixed end, very straightforward. The last time we start to derive our matrix truss member. I'm not going to detail. Maybe you can take a look of the video if you want to review how to derive the matrix. I show you the outcome. This is the matrix force displacement equations in mathematical in matrix form. And this equation is now derived in local coordinate system. What is local coordinate system? If you forget, you may take a look on the picture. Local coordinate system denoted by x prime, y prime. X prime always along the member length. That's why we call it local to the member. X prime, y prime are the local coordinate system. We derive this matrix based on the local system. This one, relatively simple. And at the same time, we can also review some terminology. Node N and node F. N means near N, F means far N. Near to the origin of the local system. Far away from the origin of the local system. N and F. We keep using this terminology throughout the entire chapters. And then after this one, I mentioned the limitation of these local equations. The limitation is that, well, if you have three members with different orientations, we cannot directly combine the equations together because they are along different directions. You need to convert the directions. This procedure is called transformations. You need to transform force displacement into the same coordinate system. Otherwise, you have no chance to put all the things together. And I remember the last time we complete these sections, right? Transformations. I derived two transformation equations to you. One is for displacement transformation equations. The other one is the force transformation equations. And then we stop here, right? No, it doesn't matter. Yeah. Here is where we stopped last time. We just derived these two equations for displacement for force and for force transformations. We seldom use them directly. Normally, they are just some equation help us to derive, move on to the next step. Okay, how to simplify our calculations? It becomes our section 4. Section 4, member global Stifford's matrix. We utilize the previous transformation matrix to convert our local stiffness matrix to global stiffness matrix. How? The procedure is quite simple. And firstly, we start from this local force displacement relationship. Small q means the local force, local actual force along the member. You can see from the picture. Q is the force along the member, small q. Capital Q used to denote the force with a sign using the global coordinate. We use small letter for local, capital letter for global coordinate. So it's quite easy to distinguish for it. Same for small d. Small d is the local displacement along at the ends of member in local system, small d. If we want to express in global system, then we use capital D. Be careful about the symbol. It means different coordinate systems. K with a prime on the top means the stiffness matrix in local system, right? This dot represents local system, K prime. So this is the local force displacement equation that we discussed in section 2. We can convert all the things to global coordinate using the previous transformation matrices for displacement for force. Firstly, we can transform displacement d, small d, to global displacement through the displacement transformation matrix T. Where to get this equation, you can go back to the previous sections. Here, T. You can convert small d to T times capital D. Actually, I just recall the formula here. This one. So in this equation, on the left-hand side is the local force. On the right-hand side, we start to express our displacement in terms of the global displacement. Global displacement means horizontal is vertical for y, global to all the elements. Then how about the force? For force, we can utilize the force transformation equation we learned in previous section again. Global force, big Q, equal to the force transformation matrix times local force. This one appeared in the previous sections when we introduced force transformations. So big Q equal to transformation matrix times Q. What is Q? Subtle Q into these second equations. And now we have a more general formula. Global force equal to a big matrix times displacement, global displacement vector, D. We can combine T transform K prime T into a single matrix. How? T is a matrix, K is a matrix, P is a matrix. So by conducting matrix multiplication 2 times, it becomes one single matrix. This may take us some time because the matrix is quite large. But if we can combine them successfully, then this becomes our new stiffness matrix K without the dot on the top right-hand corner. And now this becomes a very useful equation. On the left-hand side, it is global force. On the right-hand side, it is global displacement. So this matrix helps us to correlate global force to global displacement. The coordinate system becomes the same for all elements, horizontal for S, vertical for Y. This shows you what is big Q and big D. They are nothing but just the collection of all the global force, global displacement along at node N and node F. K, we call that stiffness matrix again, but this time is derived in global coordinate system, global system. Same to all elements. For horizontal element, inclined element, vertical element, you can use the same stiffness matrix. No need to do the conversion because it is derived in global system. We have only one global system, horizontal A is vertical Y. So it solves the problems. Right? At the beginning, we cannot combine the things together, But right now, we are along the same directions. You can use this matrix directly. I give you the answer. K. The global stiffness matrix in nano level, small k, is equal to this one. This one is actually equal to the T transpose times K prime times T. If you have time, you may derive this using matrix multiplications. Or maybe you can use the outcome directly provided by the textbook. We have a 4x4 matrix, EA over L, and then we have big matrix, all the things are lambda. What is lambda? Lambda is called direction cosine, which means cosine theta A is cosine theta Y. Help us to do the transformation. How to find out lambda? You can use the coordinate, right? As n, you have the coordinate, xn, yn. As n, we have coordinate as well, right? By using the coordinate, you can find out cosine theta A is cosine theta Y easily. L means the length of the member. If you have 2 points, you can use this formula to find out L. So lambda x, lambda y are not unknown. They are not divided. And then you put them into the matrices. You can see they are totally 16 elements right here. But if you take a close look, to this matrix, you can see that actually there are only 3 combinations: lambda x squared, lambda y squared, lambda x, lambda y. Actually, among these 16 elements, there are only 3 patterns: lambda x squared, lambda y squared, lambda x, lambda y. So they have only 3 different values, some positive, some negative. This is the first observations. Second observations, stiffness matrix. Last time I showed you some remarks indicating that all stiffness matrix should be symmetrical. Symmetrical means if you know 1/2 of the matrix, you can use the mirror image, project them to the next size, to the adjacent size. Then it can form the whole system, whole matrix. But actually, you don't need to evaluate all 16 terms. You just need to evaluate one triangle, and then you can use the symmetrical property to find out the remaining half. Okay, this is also some shortcut, help you to finish the calculations. Not all the things are new. Okay, you can use symmetrical to immediately obtain the other side. This is another observations about these equations. 3 patterns, symmetrical, and then what next? The last one is about the index on the top and along this column. What are they? You can see that matrix is what? Matrix is talking about some force, right, at different positions, different degrees of freedom, simply speaking. Nx and y represent their positions. Say, for example, Nx means these directions. N along the x direction, we call it Nx. Ny, Nx, and y. This index helps you to identify which direction they are referring to for this matrix. Now, later on, when we discuss some example, then you will know more about this arrangement. It depends on how you set up the degrees of freedom. Some further discussions. This one is about the physical meaning of the stiffness influence coefficients. The element inside the stiffness matrix is called stiffness influence coefficients. They are talking about the force induced by the unit displacement. Last time we also mentioned this term using the local stiffness matrix. For this global matrix, they have the same meaning. If you impose a unit displacement along the nx direction, evaluate all the forces at 2 ends in global system. Then it becomes the first column. You can use this definition to derive the stiffness matrix if you like. Impose unit displacement at all directions separately, and then evaluate the corresponding forces. Put them into the matrix side by side. Then you can also form the whole stiffness matrix. For some complex structures, maybe this is also one efficient way to derive the matrix. So in this part, we successfully convert our equation from local system to global system. Now we have a general formula to be applied to all structures, stick elements, no matter how they oriented. We understand some concept about matrix transformations, and we know the expressions of member Stevens matrix of trust element in global system. Try to remember this useful slide, page 51. You need to use this equation many times. If you want to solve trust problem, we have to use this equation. Then in section 5, I showed you how to combine the matrices together. Right? At the beginning, I showed you the concept. Simplest method means we consider each element and then group them together. This part, I showed you how to group all the element matrices together into a big structured simplest matrix. I use the same example. We have a simple trust structure composed of 3 trust members. Element 1, element 2, element 3. Okay, this is our element arrangement, 3 elements. And then we have 4 nodes. Node 1 here. Node 1, node 2, node 3, node 4. The number within the circle represents the node name. Node 1, 2, 3, 4. The arrangement of the node actually is not very important, but I just follow the arrangement here. So we have 3 element 4 nodes. I also show you the member orientation, and I show you red arrows. What are the red arrows? The red arrow show means the code number, the degrees of freedom, right? Degrees of freedom. We have totally 8 degrees of freedom for this problem. Because we have 4 nodes, each node we have 2 degrees of freedom. So 4 times 2 gives you totally 8. We have 8 degrees of freedom. And then we put some number to denote their position. I start from here: 1, 2, 3, 4, 5, 6, 7, 8. We have totally 8 possible degrees of freedom. 4 node times 2. How to arrange their number? Later on, I will show you an example to let you know how to arrange the order. But in general, the order of the code numbers is arbitrary. You can define your own arrangement. But some arrangement will be more efficient when you do the calculations. We will discuss a little bit later. And anyway, let us follow this arrangement. According to the previous procedure, we have the globals, we have the element Simplest matrix in global system. The 4x4 matrix. Firstly, we need to evaluate the element Simplest matrix for all elements. Small k1, k2, k3. In general, you may have n, you may have j elements in the structures. Then you evaluate all the Simplest matrix for all elements. Each element matrix is a 4x4 matrix. I showed you on the previous sections. 4x4, many numbers. Different elements may have different orientations. And then we go to assemble. Assemble means add up, grouping. Combine. This means assemble. Assemble all the things all together. Group all the matrices together. Then we call that structured Simplest matrix. Why we can add up the matrix together? Because matrix is Simplest matrix is just like a force, right? Simplest matrix just like force. We can add up force together as long as they pointing along the same direction, same positions. This arrow, this code number, help us to define their position and their directions. If they are acting along the same direction, the same position, then we can add up the numbers together. In general, mathematically, we can express using this addition operation, k1 plus k2 plus k3, and so on. Depends on how many elements we have. You have j element in this example. Then what is the dimension? What is the dimension of K? K1, K2, they are 4x4. What is the dimension of the K, capital K? The dimension of capital K, you have to, actually you can judge at the beginning. Before conducting this addition, you can immediately observe the dimension of big K. This is a very useful skill because it can help you to double check the final size of big K. How to make judgment? The size of big K depends on the numbers of degrees of freedom. Using the example on the left-hand side, what is the number of degrees of freedom for these structures? 8. We have totally 8 degrees of freedom. So once you add up all the element matrices together for this problem, the matrix becomes 8 by 8. Big K is 8 by 8 matrix for this example on the left-hand side. So the highest number, the maximum number here, should give you the idea about the size of K. K is a square matrix, and the number equal to the degrees of freedom. So before conducting this operation, you know the dimension. N by N in general. Size of structure sequence matrix, big K, equal to the highest core number. But don't worry, although the matrix look quite big, quite large, 8 by 8, but not all the elements are useful. Some of them and most of them are useless, I can say it this way. Only a portion is useful for you to solve the problems. You can formulate the global force displacement equations Q equal to KD if you have the matrix K. I'm going to show you how to solve this problem on the next sections. This section we focus on matrix assembly. Next section we will start to solve this force displacement equations. We have two examples here. Let you know how to add up all the element matrices together. Explain in detail in this example 1. Example 1 shows us a relatively simple structures composed of 2 members. Number 1, number 2, 1 inclined member, 1 horizontal member, 3 nodes. In these questions, we just asked to find out the structure sequence matrix. Okay, we just want to find out the big K in this problem. We are not asking to solving the structures, finding the response of structures. Actually, in this example, you cannot find out the response of the structures. Response means displacement, internal forces. You can't find out their values because actually I did not give you the force. I did not give you external force, so you can't solve this problem. Or maybe you can think in the other way. If there is no force, that means no internal forces, no displacement. This example just practice how to find out the K. We can decompose our calculation into several steps. Step one. I think step 1 is actually the most important step. Step 1 is to discretize structures and assign a appropriate number. Normally, students need to think about these procedures. The other procedures are pretty straightforward. You just follow the expressions of matrix, solve it, and then it gives you the outcomes. But at the beginning, you have to think about how many elements we have, how many nodes we have, how to arrange the orientation of member, how to arrange the code number, etc. We have to think a little bit at the beginning. So in step 1, discretizations, what I will do, in this problem, I give you 3 nodes. Node 1, node 2, node 3, which means that we can divide the structures into 2 elements. Element 1, element 2. This is quite straightforward, right? Element 1 and element 2. Why I mentioned this one because actually, if you want to know more about the structures, you can add some intermediate node. You can divide this infinite member into 2 elements. Why not truss element? You can use the same equations. Theoretically, you can divide this element into 2, into 3, into 4, and so on. Theoretically, but to make the calculation easy, I just cut it into 2 elements, 1 and 2, 3 nodes. And each node we have 2 degrees of freedom. Remember that we are playing with truss. Truss structures for 2D truss structures. I should say it this way. For 2D truss structures, each node contains 2 degrees of freedom, one horizontal, one vertical. Each node we have 2 arrows. We have 3 nodes, 1, 2, 3. Each node 2 arrows, which means the degrees of freedom is equal to 6. We have maximum of 6 degrees of freedom in this plot. You can observe this number at the beginning. We do no calculation at this stage, but we immediately understand the maximum degrees of freedom, 6. And another question is, we have to assign code number 1, 2, 3, 4, 5, 6 for each red arrows. How to arrange the order? The textbook gives you some suggestions. I just follow the textbook suggestions at this moment. What the textbook suggests us to do? The textbook suggests us to make some observation first. Right? We have totally 3 nodes. And some coincide with the support, some are totally 3. The textbook would like to request us to find out the positions with unknown displacement first. Unknown displacement. If you use the terminology before, which means that you need to identify the positions with unconfined degrees of freedom. Okay, if you want to use terminology. For me, I just use unknown displacement. I think it's more easy to remember. Among these factors, where we have unknown displacement, we have totally 6 possible movements, 6 degrees of freedom. We can always start from support. Support is easy to observe, I think. And support, pin N. What is the movement at pin N? Pin N prevent horizontal and vertical displacements. So at pin N, we have 0 horizontal, 0 vertical movement. Technically, pin N, we have 2 constrained degrees of freedom. Not 3. Not 3 is another pin N. So we have 0 and 0. What about node 2? Node 2, no support, right? We have no support at node 2. Node 2 is a free N. So free N is free to move horizontally and vertically. So at node 2, node 2 contains 2 unknown displacement. This is the skill that you have to develop. You have to know how to identify where we have 0 movements, where we have unknown displacements. That's why you have to be familiar with the support conditions. I have one page showed you the support condition last time in the introduction notes. You may go back to there if you have a look again. So why it's important? Because according to the textbook suggestions, they would like to assign code number at the positions with unknown displacement first. So according to the textbook method, we assign our code number starting from the position with question mark. We have 2 question marks here. We have 2 question marks, one horizontal, one vertical. Normally, we start from the horizontal direction first. Normally, if we have 2 question marks at the same node, then normally we start from the horizontal. Horizontal for X, we normally start from X and then to Y. That's why I use 1, 2 here. 1 and 2. Horizontal for 1, vertical for 2. Okay, this is why I set 1, 2, and node 2. And what about the remaining 4 arrows? The remaining 4 arrows you can assign arbitrarily because they talking about 0 displacement. So I pick up 3, 4 at the 3, and then 5, 6 at the 1. This is how we set up our code number diagrams. 1, 2, 3, 4, 5, 6. We have totally 6 degrees of freedom. The maximum number is 6. Okay. Later on, I will show you what happens if we change the code number order. Actually, this statement is not necessary. You can assign code number in random manner. I will show you what happens if you do so. But I can tell you that no matter how you arrange the code number order, you always get the same answer, same displacement, same internal force. It makes sense because the code number should not affect the result, right? If it is under applied force, like node 2, then no matter how you arrange the number, you should get the same actual force, same displacement. Code number will not affect the answer, but it may affect you how to formulate the Sylvus matrix. Normally, we pick the origin of our global system at the bottom left-hand corner here, so that all the coordinates become positive. Just make our calculation more easy. We don't want to handle negative coordinate. So I put our origin at the bottom left-hand corner. What is the coordinate at node 2? 0, 0. What is the coordinate at node 3? 3, 0. Coordinate at node 1? 3, 4. If you know the geometry, after selecting the origin, then you can assign the coordinate immediately. If you know the coordinate, you can calculate direction cosine, lambda x, lambda y. Well, next we have the node. Arrangement. We know the code number orders. The next one is to identify the member orientations. The yellow arrows represent the member orientations. Normally, I arrange the member orientation from left to right, from bottom to the top. This is how I normally arrange the member orientation. I try to arrange in this way if possible. But you can see that later, sometimes it's not possible. But again, the member orientation will not affect the answer. You always get the same displacement and same internal force, no matter how you arrange the member orientations. The member orientation will affect what? The member orientation will affect how we define the local coordinate system. The member orientation actually defined this way. The member orientation, you can think that it is the x-prime axis. If you know the x-prime axis, then you will know where is the near end node, where is the far end node for each element. Right? What is n? What is f? N means near end node, f means far end node. Right? Near what? Near to the origin of the local x-axis. And what is far? Far means the far away from the local coordinate system. The arrow points to the far end nodes. So this arrow will help you define where is the near end, where is the far end for each member. Each member, you have to evaluate for each member. Each member have different definition of node n and node f. So this is what I call step 1. Step 1, you have to define symbol, define the code number, define the member orientation. Once you have this basic set up, you can follow your arrangement and then solve the problems. Again, you can change the code number order, you can change the member orientation. It doesn't matter. But when you do the calculation, remember to follow your definition. If you change the arrangement, it's okay, but you need to follow your definition to do the whole calculations. The more things in this problem, we just want to know the structural Sylvus matrix. But to do so, we have to firstly find out the elements Sylvus matrix for all elements. We have 2 elements here. We have to find out K1, K2, and then combine them together. K1 is a simple horizontal member. You can see that we like to handle horizontal or vertical members. Why? Because if you consider horizontal or vertical members, 1 lambda becomes 0. Okay? What is lambda? Lambda is direction cosine. According to our discussion, I think in section 3, once you know the coordinate of a member, say for example, for this member, I just extract this picture from the previous slide. You can go back to the previous slide to see the whole structures. This is the member orientation, pointing from left to right. Member orientation. The arrows point to node F. The starting point of the arrow is our DN node N. Okay, that's why we have N and F. They're important, they're very important, N and F. If you confuse the definition, then you always encounter some problem about the sign, positive, negative. Why is it important? Because the coordinate as node N, we call it xn, yn. The coordinate as node F, we call it xf, yn, xf, ynx. It's quite difficult to pronounce. And you can see that when you calculate lambda, when you calculate direction cosine, we use the coordinate at node F minus the coordinate at node N. When you calculate lambda x, we use xf minus xn. When you calculate lambda 1, we use yf minus yn. We use the f coordinate minus the n coordinate in the numerator. That's why if you confuse the definition of n and f, you will probably get the wrong answer. If you have wrong lambda, then you know your matrix may have something wrong sometimes. And according to the previous slide, you can define the coordinate for each node. Right? Nx is xn is 0, yn is 0, xf is 3, yf is 0, just based on the previous coordinate. So when you put all the numbers right here, then we have lambda x equal to 1, we have lambda y equal to 0. 0 minus 0 over 3 equals 0. But actually, for horizontal member or for vertical members, one is 1, the other one is 0. That's why we quite like to handle vertical or horizontal member. Because for horizontal and vertical members, one lambda is always equal to 0. However, for inclined member, left element 2, both are non-zero, which makes the calculation more complicated. So once we have lambda x on the y, substitute their numbers back to our global element surface matrix. We use the global element surface matrix. Put that into the matrix, then we will have this element matrix in global system for element 1. This is what it looks like. I extracted from the previous sections the element matrix that we derived in section 4, right? Section 4. Lambda A squared. When I do the calculation, you can see that the equation we extract A over L outside the matrix. But in this answer, you can see that I moved the L inside the matrix. So we have length L to equal to 3. This element is equal to lambda A squared over L over 3. Lambda x is 1. 1 squared gives us 1. 1 over 3 gives us 0.333. Lambda y 0. So the next side is 0. It just proceeds several times. Remember that I tell you some properties at the beginning, right? For this matrix, you have only 3 patterns. You can firstly evaluate the patterns, I think. Lambda x squared, lambda y squared, and then lambda x lambda y. Because we always see these 3 patterns only in this matrix. Once you know these 3 numbers, lambda x is 1, right? Lambda y 0, 0. Once you know the arrangement, you can substitute them according to the positions, according to this given formula. Right? Just put their values at the 4 positions. A little bit that may speed up your calculation a little bit. You don't need to plot all the numbers. You don't need to plot all the 16 numbers. You just need to firstly evaluate their common patterns and then assign them to appropriate positions. I think this is one way that can help you to speed up your calculation. And the second way, you can utilize the so-called symmetrical property. Because the element is symmetrical, so you just need to evaluate one triangle. and then you can reflect them to the other side, find out the missing the other side. Symmetrical. I believe that this may also simplify, speed up your calculations. So this is the element one. Not yet complete. The last part is about the index on the top. The index. In the formula, I showed you nx, ny, fx, fy. What are they? Actually, they are referring to the code number that we just defined on the previous part. The first row, first column, the corresponding index is nx. Nx means the x direction and not n. According to our code number diagrams, here, not n, x direction. The index, the code number is equal to 1. That's why first row, first column, the index is 1. And then ny. Ny, the number is 2. And so on. Okay? Each element has their own index, reflecting their position, their directions. 1, 2, and 3, 4. These indexes are all very important because they guide you how to combine the matrices together. They guide you how to form the structure sequence matrix, the big K matrix. Anyway, this is how you can get element 1. Element 1 is easy because it's horizontal. Element 2. Well, unfortunately, element 2 is inclined member. I define the orientation of element 2 in this manner. So the bottom node is not n, the upper node is not n. The member orientation, the arrows always point to n. So it's node 1 becomes our far end node. Node 2 is our near end node. The coordinate at node 2 is 0, 0, according to the geometry. The coordinate of node 1 is the width is 3, the height is 4, right? 3, 4. So we know what is fn by n. You know xn by n. You can use the same equation to evaluate lambda x and lambda y. This goes in mind if okay, it's clear now. Just use the same equation actually. I use the same equation for lambda x and lambda y. I just used it before, but we have different numbers for element 2. So this procedure is quite systematic, I think, because we can use same set of formula all the time. Except that we have different parameters to be considered. And use it carefully. Because this is an inclined member. For inclined member, you can see that lambda x, lambda y are non-zero. So when you put them into the element first matrix, this time you will see all non-zero number. You will see all non-zero number. And if you have time, you can practice. You can try to do the substitutions. Here I show you the outcome immediately. While we have all non-zero numbers for inclined member. That's why for inclined member, it's quite, you need to take some more time to compute the evaluations. But you can use the same simplifications. We have only 3 patterns: lambda x square, lambda y square, lambda x, lambda y. And then we have symmetrical properties. Symmetrical. I believe that these 2 skills are useful for you to simplify the calculations. You don't need to evaluate all 16 terms. Just evaluate one half, and then project them along the diagonal line to find out the whole patterns. And finally, we arrange the code number. Start from node n. Nx 1, ny 2, fx 5. Fy 6. Arrange the code number for each element matrix according to our code number diagram. Depends on how you define the code number. Now we have K1, we have K2. Our next task is to combine K1, K2 together into our structure stiffness matrix. But you can see that they have different positions, right? K1 consists of code number 1, 2, 3, 4. K2, element 2, consists code number 1, 2, 5, 6. So how do you add them up together? You cannot directly add them up together because they are talking about different positions. Right? 3, 4 is here, 5, 6 is here. They are different positions. You cannot directly do a 4x4 matrix additions. You have to add them up. You can add up the values together if they have the same index. What I mean is that, say for example, when you take a look of element 1, the first element, the index is 1, 1, right? For element 2, this element also has index 1, 1, which means that they are along the same direction, they are located at the same positions. So in this case, you can add up these two values together if they have the same index along the row, along the column. Based on this index arrangement, you can add up the two matrices together to form the whole structure stiffness matrix. Before doing the additions, I always encourage students to firstly get a look of the overall dimension of the structure stiffness matrix. But K is a 6x6 matrix. Why 6? Because the maximum code number is 6. This tells you our final dimension of K, 6x6 matrix. And what is the first element? The first element at the top right-hand corner with index 1, 1, which is equal to 0.333 plus 0.072. And then you just do it element by element by their positions. The next element with row index 1, column index 2, then you search for each individual element stiffness matrices to see if there is any similar element with the same index. So for example here, for element 1, we have one element with index 1, row 1, column 1. In element 2, we also have the same index, row 1, column 2. So you can add up these two numbers together. 0 plus 0.096 becomes the second element. Do these position by positions. I will show you some shortcut later, but which may help you to do these additions. If you like, you can do it this way. Just map the index and then put it into the structure stiffness matrix, just like what I did right here. You can map the index and add up the values together. But when you do computer programming, or if you use Excel, or if you want to reduce the chance of having human errors, then the textbook gives us one options. The textbook tells us that we can enlarge the element stiffness matrix a little bit to make our calculations slightly more easier. How? I put optional because this one is actually not compulsory. Just like what I did here, you can directly map if you are good in this mapping. But if you are aware about the human errors, then you may do this optional step. How? We have two element stiffness matrix, and then we realize that the final stiffness matrix should be 6x6 matrix, and all the code numbers are arranged in ascending order. Right? About the final stiffness matrix, the maximum number is 6, and the code number are arranged in ascending order 1 to 6. In view of that, we can convert our we can convert our element matrix to the same dimension with the structure stiffness matrix. We can convert our element matrix to a 6x6 matrix, same dimension with our big K, 6 by 6. You have to sort the number as well, so that the number arranged in ascending order, 1 to 6. According to their positions, you just put the number according to their position, 1, 1, 1, 2, 1, 3, and 1, 4. The blue color represents the positions of our the element 1 elements. And what about row 5, row 6? Initially, we do not have row 5, row 6 for our element 1. If there is no the corresponding number, then you can fill that up with 0. Fill that up with 0. 6 by 6. Fill up those extra rows, extra columns by 0 elements. You can do the same thing for, for element 2. For element 2, you have to add 2 extra rows, 2 extra columns at the middle. If you want to enlarge the matrix. Now we have an enlarged version of element 2. The matrix is 6 by 6, ascending order. So after this enhancement, you can see that K1, K2, they have the same size, they have the same code number arrangement, all in ascending order. This may help you to visualize which element should add up with the others, help you more easy to observe. So, for example, this one add up with this one because they have the same arrangement, and then so on. This procedure is optional, but it can help you to visualize how to combine them together. If you are using Excel, then you can add up 2 matrices together in Excel if they have the same dimensions. So, take some time to do the additions. Then finally, we got a 6 by 6 structure super matrix. Okay, this is how we get the big K, 6 by 6 structure super matrix. What we can observe from this structure super matrix. Actually, all the structures, all the Symmetry matrix are symmetrical, even though for structure Symmetry matrix, it's also satisfied symmetrical property. That's why actually you just need to evaluate one triangle, just like element matrix. For structure Symmetry matrix, it also support this kind of symmetrical property. So you can try your best add up for the top triangle, and then use a mirror image to find out the remaining half. Symmetrical. It's a very nice property for Symmetry matrix. Symmetry matrix should be real matrix, should be symmetrical. So this is the answer of this question. Example 1. Example 1, we just want to know the element Symmetry matrix, element and the structure Symmetry matrix. Okay. The code number are arranged in ascending order 1, 2. I did not put it right. One final remarks. Instead of direct mapping, instead of enlarging our element Symmetry matrix, here I give you one more options, one more method, I can say this way, how to combine element matrices together. This version, you don't need to enlarge all the elements. You can do this step by step. Say, for example, I start from element 1. Element 1 is a very nice structure, it's a very nice element matrix. They are arranged in ascending order initially. So you can easily convert this to our 6 by 6 matrix with ascending code number, right? This part is quite simple. And then what about element 2? For element 2, you don't need to enlarge element 2 because you can, from our product in step 1, from element 2, actually you can quite easy to do a map at this stage. You can map the number easily to this intermediate answer. The yellow part shows you the overlapping region. Element 2 consists of element, the code number 1, 2, code number 5, 6, or the mixture of them 1, 2, 5, 6. So when you combine this element 2 into element 1, only the yellow region, you need to do some calculation because they're overlapping with code number 1, 2, 5, 6. Code number 3, 4 does not appear for element 2. So the element along code number 3, 4, you can keep it the same. Keep it the same. No change. Just need to consider code number 1, 2, and 5, 6. This is also one way how to add up the element sequence combinations together without enlarging all the things. Okay? So it depends on your options. You can do a direct mapping if you're familiar with doing these calculations. You can do a direct mapping, or you can enlarge all the matrix with the size of structure sequence matrix to do additions, or you can do this step by step. Do one and then add up the second one to the previous answer. You can add them up in step-by-step manner. It should give you the same answer if you follow the procedure properly. Okay, it's already 11 o'clock. Maybe I give you a short break. I give you a short 5 minutes break. Hello? 唔好意思，可以細聲少少，我哋嗰度好大聲。唔好意思，唔好意思。好，唔好意思，唔好意思。我哋嗰度好似個喇叭爆出嚟。係有係咪問題？ Yeah, during the break, if you can also get a look of our previous discussion to see if any questions. You may also ask the questions. I'm here. 好，唔該晒你。點啊？係咪有問題啊？哦，你係咪講 near and final 嗰個？near and final 咧，其實就係睇下你點樣定義個 member orientation 嘅，即係咧個箭嘴黃色呢一個，我哋叫做 member orientation， 即係個 member 點樣指啊？咁個箭嘴指住嗰個咧就係個 F， 個箭嘴另外嗰邊起點嗰度咧就係個 N， 睇下你點樣定個 member orientation 嘅啫，其實。唔會錯嘅，冇錯嘅，好似我啱啱講啦 ，code number 嘅次序同埋 member orientation 係唔影響你嘅答案嘅。你反轉咗冇所謂嘅，咁你咪照跟住你反轉嗰個做法做咯。唔使㗎，唔使㗎，照做到㗎。得㗎。我陣間 tutorial 嗰度會有個 example， 咁我會做個 example 3次，我試唔同 setting 俾你睇嘅。咁睇完嗰個 example， 咁你會再清楚少少嘅。咁而家我答你就係你反轉咗咧，其實唔影響個計算，唔影響個答案嘅，即係唔影響個 final answer displacement and forces。你最後個答案唔影響嘅，但係會影響你中間嗰啲 matrix 計算啊，影響你點樣去冚個 matrix 啊嗰啲咯。佢哋諗翻嚟嚇。係啊。呢個最簡單其實。我啱啱開頭提咧，其實第一個 step， 你點樣去拆個 structures， 點樣去定一啲 code number， 點樣去定個 member orientation， 其實就係你要諗嘅地方，即係你要諗下嘅地方。其實都冇就嘅，你大體上都係照塞嗰啲 equation 度嘅。反而第一步你就要諗下，我點樣定個 orientation 會好計啲咧？點樣 assign 個 code number 會好計啲咧？咁呢一度可能就要花就諗一諗咯，係。可能花陣咁，咁你計咪一開頭白紙嚟㗎嘛，乜都冇㗎嘛呢度， 咁但係我哋就有個 discussion 啱啱就咁佢哋定 cut 咗做兩個 element 之後，咁你就知道係有幾多個 degree of freedom 啦，有6個 degree of freedom，但係你唔知邊1、2、3、4㗎嘛。咁通常我哋就係由啲 unknown displacement 嗰度擺起嘅。咁呢個 structure 嗰度，咁我哋知道 log 2係 unknown displacement 啦，咁我就由左下角嗰度擺嘅1、2。咁剩翻嗰4格嘅就係 arbitrary 嘅。咁我點樣擺啦？譬如我呢度3、4、5、6。咁你話如果我倒轉得唔得啊？上邊3、4，下邊5、6得唔得啊？咁其實一樣計到嘅，一樣計到。咁然後定咗個 code number 之後，咁就再定 member orientation 咯。咁 member 嚇？點樣你可以咁講嘅，有幾多個 possible displacement 咯？有幾多個可能存在咯？moment 唔計 ，trust 唔計 moment 嘅嘛 ，trust 變咗係 trust 冇 moment，trust 就係計，即係你一開頭就係要 cut element 啦 ，cut 完你知道有幾多個 node，有3個 node 喺呢度。咁如果 trust 嚟講，每個 node 有2個佔序啊嘛，咁需要 total 6咯。同埋點解你話個 number 唔影響個計算咧？因為其實你去到冚 matrix 呢一度咧，啱啱提到咧，其實你冚 matrix 你係要將個 matrix sort 佢嘛 ，ascending order。咁 sort 完之後，咁你之前點擺個 code number 嘅，咪呢度咪跑翻正嘅都會，你全部變翻順次序咁咯。咁之後我哋嘅 example admin tutorial 嗰陣時就會再講多少少嘅。So is there any more questions? It's good to ask questions. Because according to the time now, it's already 5 minutes, so suppose we need to proceed our discussions. Is there any other questions regarding to the previous discussions? This concept, seamless method, is useful because you can see that in the next topic, theme element, we use the same method, same approach. In the next topic, frame element, we also use the same approach, discretizations, and then find out the element matrix, add up together. Which means that if you understand this concept, you immediately understand the first 3 topics. One concept, 3 topics is quite efficient. Okay, well, let's continue our discussions. Let me show you the screen. This is the second question. Before the break, we finish the discussion. For example 1, relatively simple 2 element trust structures. In element 2, in example 2, we try to consider slightly more complex structures. This time we have a complex trust composed of 6 members. One support is P, one support is rho, is lying on a vertical wall. The dimension is 10 meter by 10 meter, a big truss. Again, in these questions, we just want to know the big K. Big K. How to find out the structure matrix for this compact truss. Actually, it's not that complex, but it's quite a lot of elements, 3 times more than the previous example. But the beauty of this method is that you can always apply the same procedures, no matter how it looks like. What I mean is that step 1, discretization, assign the code number, assign the member orientation, right? And then step 2, find out the element matrix for all elements. And then step 3, add up all the things together. Same procedures. That's why seamless method is quite systematic, no matter how it looks like, although it involves quite a lot of matrix operation. Okay, let's have a look how we can deal with this problem. I talk more about the first step, discretizations. Well, firstly, we have 1 structures, we have totally 6 members. Suppose there is no overlapping at the middle. There is no overlapping at the middle. The 2 diagonal elements, they are separated. They are separated, no overlapping. That's why there is no intermediate node at the middle. Okay, this is the picture. How it out. So we have only 4 nodes. indicated by the red box. For nodes, how many degrees of freedom we have? For trust structures, we have 2 degrees of freedom at each node. We have 4 nodes here, 4 times 2 plus 8. So we can see that we have at least 8 degrees of freedom in this form. In the other words, the K is 8 by 8 matrix. Before doing any calculation, you need to know the dimension of the big K. Next, you can arrange the element notation, you can arrange the method orientation, you can arrange the node number. At the beginning, I give you nothing. So in this case, you have to define yourself. I define the element number in this way, element 1. I use the square to denote the element notation. Element 1. Element 2 is the inclined member. Element 3, 4, 5. 5 is another inclined member. And element 6 is the vertical member. This is my notation. When you do this example at home, you can try to change the element arrangement. Just help us to do that for our easy communications. When I talk about element 1, you know where it is, right? It's better than just saying horizontal vertical element. It's quite difficult to communicate in that case. And then I divide the node number, node 1, node 2, node 3, and node 4. Also for easy communication. Element orientations, the member orientations. I use a purple arrow here. Normally, when you assign member orientation, it's also based on your choice. But normally, I arrange from left to right, from bottom to the top if possible. I normally arrange in this manner. It makes my calculation slightly more easy in this case. But in this problem, you can see that sometimes it's not possible. When you consider element 5, then you cannot along the positive directions. So for element 5, we have no choice, we're pointing downward. But again, it will not affect the calculations. You can always get the same displacement, same reaction, same internal forces. So don't need to so worry about the member orientation. If possible, you can point from left to right, bottom to top. But if not possible, then it doesn't matter. Just put the arrow. Just the important thing is that after defining the member orientation, always use the same picture. Use your definition in your calculation. Do not change the direction suddenly during your calculations. When you change the orientation suddenly during your calculation, then it will give you error. The wrong result. After define this symbol, no change. Okay. We need same degrees of freedom. Right. We notice that we have only 8 degrees of freedom, 8 arrows. But where is number 1? Where is number 2? Right. We have to arrange the number. Otherwise, we cannot add up the matrices together. How to define this number? 1, 2, 3, 4, 5, 6, 7, 8. If you want to follow the textbook method, then you can do observation to see where we have unknown displacement. In this problem, we have totally 8 arrows, 8 degrees of freedom, 2 at each node. Well, the trick is quite easy. You can identify point to point, arrow to arrow. I start from node 4. Node 4 is the top left-hand corner. 3n. For 3n, free means free to move. Free to move, you have no idea about the horizontal, you have no about the vertical movements. 2 question marks. Same for node 1. Node 1 is another 3n. So we have no idea about the displacement at node 1. 2 question marks. At this stage, we have 4 question marks. We have 4 unknown displacements. Then node 3. Node 3, Pn. Pn means we have basically no displacement normally. unless you have some movement for the wall. Otherwise, we assume that there's no any displacements. Zero horizontal, zero vertical, to zero. What about the roller support? At the bottom right-hand corner. Look at this green color. Roller support lie on a vertical wall. We can see that the roller here cannot penetrate into the wall, right? They cannot move inside the wall. So you can see that the horizontal displacement is equal to zero in this case. Roller support depends on how it is oriented. This time we align on a vertical wall. So the horizontal displacement is zero. The roller cannot go inside the wall. Well, it can move vertically without any restrictions to roller. So the vertical arrows is question mark in this case. Okay, you have to identify where you have question mark, where you have zero yourself. In this problem, we have 1, 2, 3, 4, 5. We have 5 question marks, which means that we have 5 unknown displacements. We have 5 unknown displacements to be solved in this problem. That's why we call that complex. Too many degrees of freedom, too many unknown displacements to be solved. We have only 3 zeros. So go back to the original problems. How to arrange the degrees of freedom number? 1, 2, 3, 4. We start from the position with question marks. Okay? We start from the position with question marks. 5 unknown displacement to be solved. 2 at node 1, 2 at node 4, and 1 at node 2. Be careful about the one that are located at node 2. Vertical. So in this case, I start from node 1. I use number 1, number 2 for node 1, number 3, number 4 at node 4. They are question marks, right? And then I use number 5 for the vertical degrees of freedom at node 2. Because the vertical direction and the roller support become question mark in this example. Be careful about these degrees of freedom 5. 1, 2, 3, 4, 5 are used to denote the positions with question marks. They are representing the unknown displacement. And what about the remaining 3? The remaining 3 numbers, 6, 7, 8, denote the zero displacement positions. So I also start from node 2, 6, 7, and then 8. This is how we set up the code number diagram according to the textbook suggestions. Textbook suggests us to assign code number, assign degrees of freedom, starting from the position with the unknown displacement. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Be careful about node 2. Node 2, the arrangement a little bit different. We start from the vertical and then horizontal. We use the same code number diagram in the whole question 2, example 2. This is step 1. Step 1, discretization, assign the number orientation, assign code number. Okay, step 1. Step 2. Step 2, we consider each element separately to find out the element matrices. Step 2 takes us I believe there's a square of time because we have totally 6 elements. In the quiz, in the exam, don't need to solve in the quiz or examination, they will not give you this kind of complex problem because too many elements. We do not have enough time to do the calculations. In the test or examination, normally I think 3 members are normally sufficient. Okay, not too many. Otherwise, no time to complete all the things. But anyway, this example 2 just showed you what happens if you have trust structures with many members for illustration purposes. One thing that for quiz exam, I will not give you this kind of complex problem, but it doesn't mean that for assignment we can't use it. For assignment, I can give you this kind of complex problem. Because for assignment, you have more time to do. Right? For assignment, normally you do not have the time constraint. And if you for assignment, normally I allow students to use some software to support your calculations. If you like, you can use Excel, you can use MATLAB or some other software to do the calculations. I will talk more about assignment later. We have two assignments, right? One for civil cycle, the other one for structural dynamics. So go back to the problem here. Quite similar to example one. Here we consider each element, side person, use the same elements matrix on their arrangement. Element one is horizontal member. For horizontal member pointing from left to right, you notice that number one and number 8 is 1, number 1 is 0. All nice for horizontal or vertical members. Because for horizontal or vertical member, one number is 1, the other number should be 0. Going into the elements matrix. For element 1 located right here. Element 1, the member orientation points from left to right. It shows us that the left-hand side should be node N, the right-hand side is node N for element 1. The member orientation always points to node N. But the member orientation here, this one, the arrow points to node N of that member. And then the other side should be node N, D and node. So what is Nx? The code number corresponds to the Nx direction is 1. Ny, 2. Fx, according to the picture, Fx here is equal to 6. And then Fy, 5. The code number order is 1, 2, 6, 5. 1, 2, 6, 5. This arrangement based on your code number diagram. This order based on your code number diagrams. 1, 2, 6, 5. It helps you to combine the matrix later on. When you combine all element matrix, you have to add up the value with the same index. So repeat this calculation 5 more times. For element 2, element 3, 4, 5, 6. Here, if you have time, we have a look. Here, I'm not going to discuss in detail because just repeat the things 5 more times. And give you the answer. You may double check if you have time. Repeat the same calculation 6 times in total. Then you got all the elements matrices K1, K2, K3, K4, K5, and K6. The next part is to add up all the matrices together. In example 1, I showed you different ways to add up the matrix. Right? You can enlarge all the element matrix to 8 by 8 matrix if you like, or you can directly add up together based on their index. This is the final outcome. If you have time, you may try to do this, add up all the things together according to their positions. Then this becomes the final outcomes. We have an 8 by 8 structured surface matrix. A fixed element matrix. Again, it supports the symmetrical properties. All structured surface matrix is symmetrical. After your calculation, if you find that your matrix is not symmetrical, that means you do something wrong in your calculation, in your additions. If you calculate 1/2, project to the other side, to find out the remaining part. This is the K, for example 2. And later you can see that not all the elements, how many elements we have? 8 by 8, 64. Right, we have 64 elements here. Not all the elements are useful. Some of them cannot help us to solve the problems. Okay, not all the elements are useful. some are basically useless. In the next part, we will discuss how to solve a structural problem using this Matrix method. And then I will also let you know how to identify which part is useful, which part is useless in the calculations. At this moment, we can't solve the problem because we do not have the loading, no force. This page shows you the remarks. The Cope-Lambert system is just some number help you to define the directions of degrees of freedom. You can assign the Cope-Lambert in arbitrary manner. Actually, there's not necessary to follow the textbook suggestions. But in my presentation, normally I follow the textbook suggestion to keep the content consistent. Okay, just for consistent purpose. The Cope-Lambert is independent of the local elements numbering system, and there's no any inherent restrictions to arrange the Cope-Lambert. That means you can assign the Cope-Lambert arbitrarily. You don't need to follow the Cope-Lambert right here. If you have time, I always encourage students that if you have time, you can change the Cope-Lambert arrangement using your own method to assign the Cope-Lambert and redo the questions again. The Cope-Lambert should not affect the answer, should not affect the reaction, should not affect the displacement. If the Cope-Lambert will affect the displacement, that means you did something wrong in the calculations. This kind of symbol should not affect the answer. And the other thing is that when you combine the matrices together, so normally all the elements should be located along non-zero elements are located along the diagonal line, and the other side normally is zero. But actually, it depends on how you set the Cope-Lambert. But it's nice if you can converge all the non-zero numbers along this diagonal line, because this can simplify the computer calculations. When computer calculates this matrix, if you can centralize all the non-zero numbers along this diagonal line, then it will make the computer calculation in a more efficient manner. It depends on how you set up the Cope-Lambert diagrams. So in this part, we introduce how to assign Cope-Lambert for structures. We discuss how to calculate the element matrix. We discuss how to combine element matrices together to form the whole structures list matrix in this part. Wow, section 6. Section 6 is the most important part because it lets us know how to apply this stiffness method to find out the response of truss structures. In this part, suppose we know how to evaluate the structure stiffness matrix K. If you have K, how to use it to solve a structural problem for truss structures? This is something we want to discuss in this particular sections. Some brief introductions. Before showing the example, there are great examples within these sections, just an extension of the previous two. The previous two examples I just stopped at the stiffness matrix. I did not proceed to the following calculations. I will continue right here. There are some introductions. Our target, if you want to use stiffness method to handle this kind of track analysis, our target is to set up our global force displacement relationship. I hope you still remember what is capital Q and capital D. We have seen these two terms at the beginning of this lecture. They are the global force vector and global displacement vector. For example, for these truss structures, we have 8 degrees of freedom, 8 angles. K is the structure stiffness matrix, the one that we discussed in the previous part. Q, nodal force vector in global coordinate. D, nodal displacement vector in global coordinate system. What are they? Q1, Q2, Q3. What is Q1? Q1 means the possible force applied along direction 1. Q2, the possible force applied along direction 2, and so on. Q3, Q4, Q5. Q actually means the corresponding nodal force along that particular direction. 1, 2, 3, 4, 5, 6, 7, 8. We express them symbolically. So we have this nodal force vector. Q1 to Q8. We have totally 8 degrees of freedom, 8 numbers. We express them symbolically. At the beginning, then what about D? D. Similarly, D means the nodal displacement. D1. D1 means the possible displacement along direction 1. And then D2, D3, D4, D5, and so on. Oh, D3. If you express all the possible nodal displacement symbolically, it becomes our nodal displacement vector. It's not quite complicated at the beginning, right? But look on the problem again. Look on the problem again. We have totally we have totally 8 degrees of freedom from D1 to D8. But some of them are actually equal to 0, right? When we discuss how to assign code number order, code number, what we do, we take a look on the support condition to see which displacements are equal to 0, right? So here at the beginning, we express everything symbolically, D1, D3, D3. You can replace them using the exact number. Some of them is known at the beginning. Say for example, what is D1? D1, node 2. We simply said node 2 is a free end. Free end means free to move. D2, we also have no idea about what is D2. Right? D1, D2, 2 question marks because they are at the free end. Then what is D3? Pin support. Pin support gives us 0 horizontal movement. So D3, the exact value of D3 is 0. D4, 0. Then the remaining 4 are all 0. Right? 0, 0, 0, 0. So don't be scared by the notation. Actually, quite a lot of them are well-defined along our displacement vectors. Then what about force? For force, you can do a similar things. For force, we change the symbol Q1, Q2. Q1 means the applied force along direction 1. Q2 is the force along direction 2. What is Q1? What is Q2? In this question, I cannot tell you exactly, but in this question, you can see that we have one inclined force. We have one inclined force. You can resolve this inclined force into the horizontal and vertical components. Maybe I call this FAs or F and FY. You can resolve an diagonal force. The applied force should be even. Right? F should be even. Should be 10 kilonewton or 100 kilonewton. Without applied force, there's nothing to do. You can resolve this diagonal force into horizontal and vertical component. Then it becomes our Q1 and Q2. They are well defined, okay, based on the given force value. What is Q3? Q3 means the nodal force along direction 3. Q3, Q4. Q3, Q4. What is Q3, Q4? Do you know the values? Q3, Q4. We don't know the value because Q3 actually is the reaction. Q3 is the reaction. Q4 also the reaction and the pin support. Similarly, Q5, Q6, Q7, Q8, they are reactions. We don't know support reaction at the beginning. If you know the reaction, then you don't need to do the check analysis. So Q3, Q4, Q5, Q6, Q7, Q8 are unknown benchmarks. Some that we want to solve. Unknown. Now, F, X, F, Y are well defined, although I did not give you the number. In reality, you should know the loading, 100 kilonewton or 200 kilonewton. Put the given informations back into these equations. K is unknown. When K is unknown matrix, Stippler's matrix, we derived it in the previous sections. So in this problem, you are asked to solve the unknown displacement, D1, D2, and solve the unknown reaction, Q3 to Q8. You can observe one very interesting pattern in this arrangement. Along the same row, if you know the displacement, along the same row, if you don't know the displacement, then on the other side, the force should be known. Similarly, if you know the force along row 3, then the corresponding displacement should be equal to unknown value. One side known, one side known. You can also use this pattern to check your answer, to check your formulations. One side known, one side known. Before solving the problem, I think it's good to check your formulations. Otherwise, you cannot get the exact answer. Some description about the meanings. On the top, along the force vector, the upper part represents the applied loading. The bottom part represents the reactions, which are known. Along the displacement vector, the upper part represents the unknown displacement, D1, D2. The bottom part represents the support displacement. Displacement and the support. Now put a remark here at the bottom. We have no displacement normally, but sometimes if you want to handle some special scenarios like support settlement or support movement, sometimes we need to consider this kind of special scenario in which support is allowed to settle. Settle means go down. If there is support settlement, then we probably have non-zero numbers. Non-zero but well defined. So we make the calculation slightly complicated in that case. So what we are going to do, firstly, based on your code number diagrams, find out the known force, find out the known displacement, and then try your best to evaluate the structure Stippler's matrix. This is what we did before in the previous lectures. I expressed them symbolically, Q1, Q2, Q3, and so on. They can find out their numbers by following the previous procedures. For matrix operations, we allow to subdivide the matrix into different small matrices. You can divide matrix vector to small matrix, small vector. We call that matrix partitioning. Partitioning means cutting. You can cut a matrix into 4 parts. You can cut a vector into 2 parts. The known force, we call that known force vector. We group the known force together, become QK. The subscript K stands for known force vector. The bottom part, unknown. Unknown, we call that QU. U stands for unknown. du is the unknown displacement vector. dk is the known displacement vector. Instead of putting down this whole big matrix equation, you can use this folded vector, express them symbolically using a simple symbol. What about the matrix? The matrix you can divide it into 4 parts. K1, K12, K21, K22. In this example, K1 is a 2x2 matrix with 4 elements.
K12 is a rectangular matrix, 2 rows, 6 columns, and so on. Then how to define the size of this cutting? How to define the size of this cutting? It's quite easy. Depends on the unknown displacement. K11, the dimension of K11 should be the same as the unknown displacement vector. The size of displacement vector is 2 by 1. 2 by 1 vector, 2. In this case, the size of K11 should be also with the same size, 2. Depends on the size of du. If you have 2 unknown displacement, then K11 should be 2 by 2 matrix. If you have 4 unknown displacement, then K11 should be a 4 by 4 matrix. The size depends on the unknown displacement. This cutting. This cutting depends on how you arrange your Coulomb diagrams. So how to solve the problems? How to solve these equations? I express the equation symbolically. At the beginning, we have a global force displacement relationship, Q equal to KD. All capital means they express in global system. We can convert them using matrix partitioning, cut them into known, unknown, known, unknown, and known. Okay, just based on the previous discussions. Cut them into the known part and unknown part. And then by using matrix multiplications, you can convert this equation into 2 matrix equation. Equation 1, equation 2. How to do the conversions? Just one matrix multiplications. 2k, the first row here, equal to this row times this column. Matrix multiplications. Q1 and qk equal to q1 times du plus k12 times tk. Just like matrix multiplication, first row times the column give you the first equation. And then you can do the same thing for the second row to find out the expression for QU. This time we have 2 equations on the next page, obtained from matrix multiplications. I simply call this equation 1 and equation 2. Then what we do? Simplest method is a displacement method. Simplest method is a displacement method. Which means that we would like to find out the unknown displacement first. For displacement method, we would like to find out unknown displacement first. Our target is to find out Q, U, and V, unknown displacement. Which equation can help us to find out unknown displacement? It seems that the first equation can help us to find out unknown displacement. Why? Because QK means the known force vector. QK is known part. K11, K12, they are extracted from the Stevens matrix. We have Stevens matrix, although it takes some time to construct the matrix. K means known. So when you take a look on the first equation, actually, we have only one unknown vector, du. So by using the first equation, you can find out unknown displacement. Most of the time, dk is 0, just like our example before. We have no displacement and a support here. We have no displacement and a support in this example. So if dk is 0, then the equation 1 becomes even more easier, more simple. If dk is 0, then the second terms of the right hand side disappear. It becomes this equation qk equal to q1 times du. By solving this equation, you can find out unknown displacement. How to solve these equations? It depends on how you do the matrix calculations. One way is to multiply the whole equation by the inverse of q1. multiply the whole equation by inverse of K11. K11 inverse times K11 gives us what? On the right hand side, K11 inverse times K11 gives you identity matrix, which means you can ignore it. So the right hand side only have AU. Unknown displacement is equal to the inverse of K11 times the known displacement vector. That's why if you are able to find out the inverse of K11 by conducting these matrix multiplications, it gives you a known displacement immediately. This is how you can do structure analysis using matrix method, by using matrix multiplication, using matrix inverse, and so on. In the example, I will let you know how to play with this equation. Then what next? Suppose you have the displacement right now. By solving the equation, you know the unknown displacement. If you know the unknown displacement, then you can use the second equation. Substitute the unknown displacement. Now you know the numbers after doing the calculation. Put it into the second equations. It helps us evaluate the unknown reactions in this case. So you have the displacement, you have the reactions. This is normally what we want to know for structural problems, force and displacements. We want to know one more thing. Remember N force, which means the actual force along the truss member. How to find out actual force? I give you the formula. This one is our local force displacement relationship. This is the local equation, the one that we introduced in section 2 a long time before. If you know the global displacement, B, you can use the global displacement together with the displacement transformation vector matrix to find out the local displacement of a truss element. Local matrix times local displacement give you back the local force of truss member. This is how you can calculate the member actual force for each truss member. Expressed in this way: 1 at N, 1 at F. The actual force along the truss member, N and F. But there is no need to calculate both. No need to do so. Why? Because truss is actually a loaded member. If you know one side, then the other side should have the same idea, but opposite in the directions. So actually, you just need to know one. In the book, we calculate QF. In the book, we calculate QF. If you know one force, then you can automatically evaluate the other side. QF can be calculated using the second row of the previous equation in this way. EA over L are the material geometric properties of the truss member. Lambda is lambda 1 are the direction cosine of that member. Depends on which one you are going to calculate. dnx, dny, they are the end displacement of that member under considerations. Depends on which member you want to calculate. And this part, you should know the displacement. You should know the reactions. So there is no unknown displacement right here. You just use your outcome to find out the member force if necessary. Depends on what you want to know. If you get negative values, which means it is in compressions using these equations. Positive tangent, negative compressions. So here I would like to use example 3 to discuss how we can solve these truss structures using slitless method. Example 3 look quite familiar, right? Because this is actually the example 1 that we just handled before the break. 2-member truss structures. But at that time, we just saw at the slitless matrix. We did not go to the solving problems. now in example 3, we are going to solve the problems. This time you can solve it because I give you the loading. This structure with the same geometry is now under one concentric force at node 2 along the downward directions. If you have force, then you can calculate the reactions, the displacement, or the other things. Now, but in this question, I assume that we have the structure Stevens matrix. If you forget how it looks like, you may go back to example 1 to find out the expressions. Right here, I just call the structure Stevens matrix directly. And then I also copy this code number diagram from the previous example 1. We introduced how to arrange the member orientation, the code number. I just add the loading right here. This time, along direction 2, we have nodal force. We have concentric force. The value is 2 kilonewton, but in downward directions. Downward means negative. Q1 0, Q2 negative 2 kilonewton. Q1 is 0 because we do not have horizontal applied force. We just have one downward force at node 2. So Q1 is 0, Q2 is minus 2 kilonewton. And what about displacement? Displacement d5, d6, 0 because Pn. d3, d4, 0 because Pn again. So in short, d3 to d6 are 0. Q1, Q2, 0, and minus 1. At the beginning, after assigning your code number diagram, you can immediately put them down. Actually, you can put the known quantities down on your answer book at the beginning after defining the code number arrangement. TK or 0 correspond to the code number 3456. QK 0 and minus 2. Again, you can satisfy the